So if you look at this graph, what does it represent?
Duty cycle or PWM?
And what it is PWM. So today, what we'd like to do is we'd like to add a new feature into the system, which is the pulse width modulation. So the concept is very simple. I copy this one. You have a fixed frequency. So right now, look at this graph here. From here to here, or from here to here, or here to here, everything is the same frequency, right? So what's changed is the duty cycle of the active high and active low. Usually you work with active high, but you can apply the same concept if you do exactly the opposite. You cannot get the active low version. Okay? So what is it doing? This is doing a digital way of changing the duty cycle of a square wave. And then we call this pulse width modulation. Okay? So where do we use this? You use this kind of circuit to control a servo motor, or you can use this to control the brightness of the LED. So the idea is, if you want to use this to control brightness of LED, you are going to turn on and off the LED at a certain interval. So it gives you the illusion that the LED is brighter or dimmer. And again, it's an illusion because your eyes cannot respond that fast. Okay? So today, that's our goal. So before we start working on the real Q system, we're going to look at how do we do this in Quarter Street. What's the concept behind it? Okay. So that means we need to create revision number 1. So let's start with the simple concept, the counter. Okay? Suppose the counter counts from 0, 1 to 6, 7. 3 big count. Okay? So the counter is going to count 0, 1, 2, 3, 4, 5, 7. And then 0, 1, 2, 3, 4, 5, 7. And then continue. Okay, very simple 3-bit binary counter. So what we're going to do is we're going to add a signal. We call it timeout. The timeout is going to go active high whenever the count is toward the end. So right now, if you look at this, at the end of the count sequence, this is the end, this is the end. Right? So that means everywhere else it should be 0. Okay? Alright? So let's draw the waveform instead of writing out the numbers. This active low. Okay, and then continue like this. Right? So if you look at the timeout signal, what is the frequency of the timeout signal compared to the clock? Now the clock is changing every time. So every time a rising edge or falling edge, you count up, you count up. But the timeout signal is not. It is only active for a certain amount of time. So it takes 8 cycles for the timeout signal to go high. Okay? So that means the frequency of the timeout is 1/8 of the original. So if clock is equal to 1 minute, and timeout is equal to 1 mag divided by 8. Whatever that is. So you do the math, 125 kilohertz. Okay. All right? That's very simple. So on our board, we do have 1 mag. What do we have? 50. So if you feed the 50 megahertz into this 3-bit counter, what frequency do you get? Do the math, what do we have? Faster than anything. Right? 6.25 meg. Okay? Right? This is too fast for PWM. Usually PWM, like LEDs, will talk about kilohertz. Probably 1 kilohertz or a few hundred kilohertz maximum. Nobody's going to use megahertz. So now we need to bring it down even more. Okay? All right? So 6.2 meg, 2.5 meg, too fast. We need something to try 16-bit binary count. Now 50 megahertz divided by what should be the denominator? 16. Not correct. Not 16. 2. 2 is not correct. How do we get that?
0 plus 16.
No. What should be the denominator? Think about if your counter is counting from 0 to 16, sorry, 0 to 15 is now 0 to 7. You put down a number, it's 50 megahertz divided by what? 16, right? So to the power of 4. So right now, I increase the number of bits from 4 to 16, then it should be divided by 2 to the power of 16. Okay? So if you do that, what do we get?
$763.
763, that's good enough. 763 hertz. Okay? The decimal points, we don't care. So now you can feed your clock through a 16-bit binary counter, which has a timeout signal, will give you 763 hertz, which is in the order of kilohertz or few hundred hertz. So this is pretty much usable. Okay? So the first thing is you need to create a counter that is 16-bit binary up counting. And then you will time out at the end of the cycle for 1 cycle only. Okay? All right? So far, so good. So this will give us the frequency. Now, how do we manage the duty cycle? This is the next topic. Okay.
You have another counter.
Yes?
To do the duty cycle, you need another counter.
Simple as that. Simple as that. All right. So now let's draw the waveform. So now we have the timeout signal. 16 bit. It goes like this. Okay. we're going to do is we're going to have a register holding a 16-bit value. 16-bit register. So the counter is 16-bit, the register is 16-bit. Now, because they are the same width, it makes everything easier. Because when we do comparison, we're comparing 16 versus 16. Understand? So this 16-bit register is going to compare its value with the counter value. Understand? Alright. So the timeout is a representation of the counter. The 16-bit register holds a value in it, and then you constantly comparing these 16 bits versus the counter. Now, the 16-bit is not changing, but the counter is changing, right? Eventually, they will be the same, correct? All right. So if 16-bit register is less than counter, output, in this case, comparator, equals to 1, else equal to 0. Okay? Right. So what does it mean? So the comparison will give us this kind of behavior. Initially, the 16-bit register, I'm sorry, it's not less than, it's more than, or greater than. Initially, the counter starts from 0, 1, 2, 3, 4, 5, 6, 7, correct? Your register is not 0, it's some value. So for example, 200, okay? So your 200 is bigger than 0, it's bigger than 1, it's bigger than 2, it's bigger than 3, and then you end up with something like this. Eventually, the counter is going to hit 200. 201, that means your comparator will change state because you're less than 200, okay? So the output will go down, and then you go down until the next cycle is finished, which is here. And then the whole thing repeats. Understand? So you have a counter that's constantly running. You have a register, say I want this duty cycle. Give a number. This number will be compared against the counter. Understand? And then the output of the comparator is going to be the duty cycle of your PWM. If you say I want more duty cycle, that's fine. Increase the register value. The maximum you can go is FF. The minimum you go is 0000. Okay? Understand? So you have a register outputting a value compare against the counter. Okay? So what's the trick here? The trick here, you have to control this in an orderly fashion. The reason is the register that you're going to provide is by your software. Okay? Your software has no idea what the count value is. Okay? So there has to be an extra circuit that will capture the input that you have, the 16-bit register, and then wait until the timeout signal is there. Because when it times out, that means you can start over again. Understand? So that's why we need a timeout signal. The timeout signal will give the frequency as well as the signal for the state machine to understand, hey, I cannot update the 16 bits until I finish the current cycle. Okay?
Should we be constantly updating every cycle?
Yes. Every time you have a timeout, you update. Wow, if you make it smart, if you detect there's no change in the register, you don't do update. But it's okay, it's no need. If you update to the same value, then there's nothing, there's no side effect. Okay. So let's put down some annotation here. On this here, you update a 16-bit register. Update 16-bit register. We're going to put down some exception here. reason is you cannot have 100% duty cycle. Okay, if you 100% duty cycle, everything is flat. Okay, so the maximum value you can put down is the maximum of the counter minus 1. Okay, however, if you can make a programming error, you may put down FF instead of FE. So what you do, your state machine should be smart enough. If it detects the duty cycle is FF, by mistake, just put a 1 on the output instead of doing PWM. On the other hand, you cannot have 0 duty cycle. If somebody gives you 0, you just off constantly. Okay? Anything in between, that means it's a legit duty cycle. And then you can process it. Okay. Right? Let's have a problem. So let's draw a block diagram. Exactly. So now we have our this is our Q. This is our PIO 16 going out to the external circuits. Okay. And then you build another circuit that's a state machine plus 16-bit binary up current. Right. So what we'll get, you get 2 sets of signal. This one is timeout. One bit. This timeout signal is if you want to do some debugging at the end, you can put it on a pin and you can debug. But you don't need to bring it to any pin. This one is 10 LED. Okay. 10 LED. Let me go do that circuit. So this circuit we will do is first give input equals 0, 0, 0, 0. LED equals 0. And input equals 0, F, 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 F. LED equals to 1. So turn on all. Turn off all. Okay? Anywhere in between, you can go to do the PWM. Else, PWM. Just do all of them together. Just do all of them together. All right. Now, so far, any questions? So many questions. Okay. Now this one is pretty involved. You design a state machine, because the state machine has to know, hey, I have a value coming in. Right now, I can only update the value when the timeout is here. I need to wait for the timeout signal to show up first. Then I put it in. Okay. If there's no timeout, don't do anything. Just let whatever the cycle finish. Now everything is connected to the same clock, 50 megahertz. So everything is fast. Right? This need to have a comparator. 16-bit comparator. Okay. The 16-bit comparator will determine the duty cycle. So when you take the comparator does not have 10 outputs. The comparator has only 1 output. Whether the register value is higher than the count or less than the count. Okay? What you need to do is you always need to register the output. What it means is you go through a flip-flop. You cannot just do gate comparison. Always put a flip-flop. That will clean up all the signals. Otherwise your signal will be going up and down. Understand? So this whole circuit has its own clock, which they are all connected to. So this is clock diagram. Alright? Any questions? This one is quite involved, so I'll give you 2 weeks to finish. Alright? So how do you prove it is working? Okay. You go through every single combination of the duty cycle. And then you should see visually the LED is dim, off, dim, brighter, brighter, eventually it will become very bright. And then we can see actually it is working. Okay? Alright? Any questions? Alright, so let's go to the virtual machine. Let's do this to update our division. So copy everything from 12 to 13, 13, and then start with 13. So we're done with the hex. Okay. So PIO, parallel input output. And how many bits? 16. Output only. This one we use to check it. But now checking it or not checking it doesn't really matter. Okay? Even if you check it, it doesn't change anything. So this is what we have. Let's give it a name. This is LED PWM. What should be the clock? What should be the clock?
D0.
No, it's V0 system clock. Okay. Reset connection. Slave connection. External connection. Last step, remember, every time you add something, you always have to assign base addresses. Okay, always have to do that. Save and generate. So you're only adding one component this time. Done. Now, if you go back to your block diagram, at the bottom, there should be one more bus coming up. This is the one. So you cannot connect this directly to your LED because you don't have 16 of them. You only have 10. You don't go through your circuit. Understand? So let's take a snapshot of this. Put it in our notes. We'll use it a little bit out. I'm trying to I can. Oh.
So what we do first?
Yes.
Did you just add LED? PWM?
What?
LED PWM?
Yeah. LED PWM.
From where?
From here. PIO. They are the same. Under under microcontroller peripherals. Sorry. Peripherals, microcontroller peripherals, PIO. It is exactly the same thing you use to add the hexadecimal hexadecimal display.
And the width was 16, right?
16-bit. That's right. Because that's the frequency of 16-bit PWM.
Is there anything we have to change beside only 16?
16-bit check.
Check to the builder or auto?
Yeah, it doesn't really matter. You can check or don't check. It's the same thing.
Once when the Microsoft peripheral is looking for them?
PIO.
We enable individual bit setting.
We're not going to use it.
Okay.
Even though you check it, you program it, you don't use it, you